pi there. So far, we have already discussed two of the conic sections. These are the parabola, which we know to look like this, the ellipse, which we know to look like this, and under ellipse, there is the circle, which we have also discussed. Lastly, we'll now go on to the hyperbola, which looks something that we'll figure out later. Okay, so let's begin. So what is a hyperbola? A hyperbola is defined to be the following. It is a set of all points in a plane where the absolute value of the difference of whose distances from two fixed points, which we called f1 and f2 or the foci, is constant. This is what an hyperbola is. So what does that mean? That means that if, for instance, we take this point P and we get this distance out here, so let's say this one is d1 and this one is d2. If we take the difference of this one and take its absolute value, it must be equal to a constant, and this constant must be true for any point in the hyperbola. For instance, if we take this point, get its distance, let's say the distance is d3 and d4. If you take the difference of d3 and d4, take its absolute value, what you need to get is also c. Some more stuff related to an hyperbola. In a hyperbola, we have what we call the center. The center is the midpoint of a line segment connecting the two foci. If this is the two foci, this is the line segment connecting them. Just get the midpoint, which is around here. That is why the center in this case is precisely this violet point, which we denote usually by C. Next, we have the vertices. The vertices are the points of intersection of the hyperbola and the line through the foci. How would that look? Basically, this is our hyperbola, and the line through the foci is this one. So the intersection must be around here, which is precisely this V1 and V2, the vertices of the hyperbola. Third one, we have what we call the transverse axis. The transverse axis is the line segment connecting the two vertices. So if these are the two vertices, this is the transverse axis. So usually transverse axis is useful in determining the orientation of the hyperbola. One thing to take note here is that in a hyperbola, it has two asymptotes, or basically it has two lines which it never intersects. These two lines are this one and this one. So basically, what this means is that if this hyperbola extends infinitely out there, it would never cross this line. So this actually gives us an idea on how to sketch the hyperbola. If we can construct a, let's say, a rectangle out here such that its vertices is exactly where the line or the asymptotes pass through, then we could easily sketch these two parabolas out here. So we'll illustrate that later in our examples. So now that we have covered the basic stuff out of the way, let's now go on to the equation of a hyperbola. So there are two formulas for the equation of the hyperbola with center at hk. The first one is this form, and the second is this form. So take note here that the variables are x and y. The constants here are hk, which are determined by the center, and we have here a and b, which usually determines the distances from the center. The a and the b will also be useful when we construct the rectangle that we illustrated in the previous slide. So before we go over these other stuff, what differentiates these two formulas, basically we focus on where the minus sign is. So in this first formula, we have here minus with the y variable. That means if this is the y axis, the hyperbola must not intersect this one. So the hyperbola would look something like this. Okay, on the other hand, in this second formula, we have minus with an x variable, which means it's like if this is the x-axis, our hyperbola must not intersect this or pass through this. So it would look something like this one. So that is usually the markers in determining on your mind how the hyperbola would look. And from there, the foci and the vertices, the formula for this one would immediately follow. For instance, if in this first case, we know that the hyperbola would look something like this, then we know that if this is the center, HK, to obtain the foci and the vertices, so the vertices would be here, the foci would be here, what we need to shift is the x coordinate of the center. That's why what we add and subtract is precisely only on the x coordinate. The same idea applies for this second version. The transverse axis for the first and the second formula immediately follows from how it looks, and for the equation of asymptotes, this is something that you need to memorize. If you want a derivation of this one, comment down below and I'll be glad to show you one. But it's kind of complicated, technical, something that we don't really need. Take note here that the C here refers to this equation out here. So C is represented by the square root of a squared plus b squared. So take note of this one, and we now move on to our examples. Okay, so let's move on to our first example. So for our first example, our goal is to find the center, the vertices, the foci, and the equations of asymptotes of the given hyperbola x squared over 25 minus y squared over 49 equal to 1, and provide a sketch of it. Okay, so to do this, we first express this given equation into the form that we had on the formula sheet earlier. So what I mean by that is to observe that x squared over 25 minus y squared over 49 equal to 1 is the same as x minus 0 squared over 5 squared minus y minus 0 squared all over 7 squared equal to 1. So given this, we immediately know that the center must be the point 0, 0, since the center represents this 2 out here. Next, the vertices. So for the vertices, take note that since in our formula out here, we have minus the one with the y variable, then we know from earlier that the hyperbola must omit the line that is parallel to the y-axis. So if this is the y-axis, the hyperbola must look something like this. So if this is the center, what we shift is the x-coordinate to obtain the vertices, and so is the foci. Given that idea, we know that given the center, what we will change is the x-coordinate. What will we add and subtract there? That will be based on the a earlier, and in this case, the a is the 5. And 7 here represents the b. So how do we remember that one? The key is to just take note that the a is obtained from the denominator of the positive variable. So in this case, x here corresponds to the one with the positive, and y here corresponds to the one with the negative. So 5 here is the a. So adding and subtracting that here, we obtain the vertices to be plus minus 5, 0. Third, we need the foci. To obtain the foci, we also add and subtract to the x-coordinate. But in this case, recall that in foci, what we add and subtract is the c. The c is obtained by computing the following. So take note that c is equal to the square root of a squared plus b squared. Square root of a squared plus b squared is given by 5 squared or 25 plus b squared or 49. So solving this one, we will obtain 74. So once that we have this, we know that the foci is given by plus minus square root of 74 there. So we now have the center, the vertices, and the foci. Next, we go to the equations of asymptotes. So for equations of asymptotes, I suggest that you just remember the formula. So for the asymptotes, we will have here y minus the one here, this one. So basically, for the asymptote, we'll have this and this. So we'll have y minus 0 equal to x minus 0 out here. And this one will be determined by the a and the b. If you go back to our formula, what we will have is, for this case, we'll have b over a. So we'll have here 7 over 5. And take note that since we have two asymptotes, so just recall in the formula that this must be plus minus. Also take note here that to remember this one, all you need to do is check the denominator for the y over the denominator for the x. So let's keep it at that. So now that we have the center, the vertices, the foci, and the equations of asymptotes, we are now ready to provide a sketch for this one. So in sketching, my suggestion is you start by plotting the special points. So we have here the center and the vertices and the foci. So let's have here the center, the origin. Then we have the vertices, which is plus minus 5, 0. So let's see there. Next, the foci. So take note that square root of 74 is much bigger than 5. So the key there is to just observe that 5 is equal to square root of 25. Clearly, this is less than square root of 74. So by that I mean, square root of 74 would be somewhere around here. Now, how do we construct the hyperbola? The key is to construct the rectangle. So the rectangle will be obtained by using A and B out here. So take note that if A represents the horizontal distance, B will represent the vertical distance. So we'll have here probably around here and around here. Then from here, all you need to do is to construct the rectangle. Once we have this one, take note that the asymptotes will represent this one. This here will represent y equal to 7 over 5x, and this here will represent y equal to negative 7 over 5x. So you can verify that one, that this line is indeed the one that passes through the vertices of the rectangle. Once you have this, the hyperbola would be easy to sketch. It would look something like this. I think it's good enough. So this is how the hyperbola would look like. So that's it for the first example. Let's now move on to our second example. For the second example, we are tasked to find the same things or same stuff as earlier, but this time we are given a not so straightforward hyperbola this time. So how do we solve this one? Well, we first convert this thing into something that is much more familiar. So take note that we can express or rewrite this one as something like this. Okay, so how did we obtain this one? Basically, what we did is we combined the terms with the x's. So in this case, this one and this one went through here. Then we factored out negative 9. Afterwards, we moved the y's out here into this one and factored out the 4. So what is the purpose of this one? The purpose of this one is that we want to convert this in such a way that we'll have here a square of a binomial. And when we have a square of a binomial, we'll be one step closer to having the formula for the hyperbola. So observe here that upon completing the square, what we need to add out here is 4. So that this thing will be a perfect square trinomial. So since we add 4 out here, and then we have a multiplier 4 out here, to balance out both sides of the equation, we must add 16 out here. Similarly, take note that to complete the square out here, what must we add is 9. And since we have a multiplier of negative 9 out here, what we must add, or in this case subtract, is 81 to balance out the equation. Good? So once we have this one, let's simplify. We'll obtain this one. Basically, this is just a simplified version. And then for here, since this one is a perfect square trinomial, we know that we can rewrite it as a square of the quantity y plus 2, and similar to this one. Now, one last thing out here, take note that since in the formula, we know that this must be equal to 1, then we divide 36 in all sides. That will give us this one. For this first one, 4 over 36 will be 9. And then take note that we can write this one as y minus negative 2. And then for this one, dividing 36 out here will give us 4 out here. And then we can rewrite quantity x plus 3 as x minus negative 3 squared equal to 1. This one now is similar to what we want. Okay, so given this one, clearly the center is given by the point negative 3, negative 2. For the vertices, since we have the minus part to be on the x, then we know that in our hyperbola, it must omit an axis that is parallel to the x-axis. So if this is the x-axis, our hyperbola would look something like this. Which means that if this is the center, we shift its y-coordinate to obtain the vertices and later on the foci. So what will be the A in our case? Again, the A is obtained from the denominator of the one with the positive variables. So in this case, this one is the one with the positive, this one is the one with the negative, which means that our A must be equal to 3, since 9 is equal to 3 squared. On the other hand, we'll obtain B to be equal to 2. So with this in mind, the vertices will be obtained by negative 3, negative 2, plus minus the A, which is 3. So this will give us negative 3 and negative 5 with negative 3, 1. For the foci, we add here negative 3, negative 2, plus minus C. So we're just calculating it out here. So the C is given by the square root of a squared plus b squared. A squared plus b squared is basically 9 plus 4, which will give us square root of 13. And then again for the asymptotes is basically this thing out here. So we'll have here, and then for the slope out here, that is given by the one with the denominator of the y and then the denominator of the x. So we'll have here a 3 then over 2. So we'll have here plus minus 3 over 2. So now that we have this, the only thing that's left is to sketch it. So again, the key in sketching is to first plot the important points. So first is the center. Afterwards, we have the vertices, negative 3, negative 5, and negative 3, 1. Then next is the foci. So for the foci, just take note that even without computing this, we know that it must be somewhere around here. So let's say this is negative 2 plus square root of 13. This is negative 2 minus square root of 13. And then again, the key to form the rectangle is based on the A and the B. Since the vertices already represents for the distance for the A, we now move on for the B, or this time it's the horizontal distance. So shifting by 2, we'll have here negative 1 and then negative 5. Let's now form the rectangle. It should look something like this. And then let's connect the vertices. And then from here, we can now form the hyperbola. So this is how the hyperbola for this example would look like. So that's it for this video. Before you go, so kindly help me provide better math content to you by answering with your Google form in the description down below. It would be really helpful to improve the content that I provide to you. So in the next video, we'll be focusing more on more challenging examples related to hyperbola. So that's it. Have a nice day.